Hello, my name is Ignatius Garcia from Civil Engineering.
Hello, my name is Osdi from Mechanical Engineering.
Hello, my name is Pasha from Metallurgy and Materials Engineering.
Hi, my name is Diva Calista from Metallurgy and Material Engineering.
So in this video we'll look at how double integrals, and in this case the double integrals of 2xy squared over region of R, which is a rectangular region in the xy plane drawn over here. It can be calculated as an iterated integral using Fubini's theorem. First, let's just get a conceptual understanding of what it is we're really computing here. I've drawn the xyz system, and we've got the surface of z equal to 2xy squared. Just think of a surface sitting over the xy plane, and in fact, because we're living in the first quadrant here in the xy plane where x and y are both positive, this whole surface will live above the region of integration, R, which is sitting down in the plane there below. And if you look at the patch of surface that is determined up above the surface and think about the volume trapped in between the surface and the xy plane, then my double integral should be calculating that volume. Fubini's theorem says that we have to calculate this by converting it to an iterated integral. That means performing two integrations, one with respect to one variable and then with respect to another variable. So now I'm going to arbitrarily choose to integral first on the outside with respect to y, and that means my outer integral should have constant limit of integral that depends on the variable of y. If we look at our picture, the y values are varying from y equal to 1 to y equal to 2. So that as an inequality says y is trapped in between 1 and 2. And x values are trapped in between x equal to 1 and x equal to 3. So those are my corresponding x values, and understanding those inequalities and how they determine the point that live in this region R tells me how to set up my limits of integration. So my y values go from 1 to 2, so that's the y, and my x values go from 1 to 3, so that's the x. And we now calculate this integral by performing an iterated integral. We calculate the inner integral first and find an antiderivative for 2xy squared with respect to x. So I think of y squared, that's just a constant, and I integrated 2x to get x squared, and I need to evaluate that from 1 to 3. And these are values of x that need to be plugged in, so everywhere I see an x, I'll have 3 for x squared there, and I'll have 1 for x squared there, and I subtract, and y is just carry along with the calculation. Now I integrate with respect to y. After simplifying this one, we have this one, and evaluate that from 1 to 2. These are values of y. Now there's no other variable in the expression anymore, so we just evaluate that, and then we got 64 over 3 minus 8 over 3, then we got 56 over 3.
So, double integral. This is the basic premise of it. This right here. So, this is the first integral. So, the c, d, fx, the function, and dy, that is the first integral. The second integral is the a being the result of this function that you firstly got, and dx. Now, polar coordinates, this here be the function. So f equal f r cos theta comma r sin theta depends on what are the functions in it, and you can see the boundaries. For the first integral is dr, and the second integral is d theta. Now this is the graphic of it. As you can see here, it is bounded by the two thetas. One is alpha and one is beta. This here is a line, the line created by of a function, and this here is the value of a and b. So the basic premise of an integral is to find an area or an average of something. So if we have to find the average time for the vehicle So when we are in traffic, you want to beat your father in a contest. So you bet that it will only take 10 minutes for us to take there, and your father said it will take us 20. You see the traffic flow and you try to recalculate and you get 10 minutes. That's how you win, by using integrals. Finding the average and trying to find what is the most probable solution. Integrals, as you can see, we can find an area limited to a boundary. So you can see here it is bounded by these two functions and these two values. That's one of them. Another one is to find an average of something. So you want to use it to average your time? You can. So since there is an upper boundaries and a lower boundaries. Now, since the upper boundaries and lower boundaries exist, you can triangulate and try to guess which is the right one. Since this is only integral and you can only have the upper boundaries and the lower boundaries values. So if the result is 20 to 25, you can pick one of these values to get your wanting value. Depends on the situation. Like in the traffic.
Discuss about the integral surface area. Let's start with some simple surfaces. We have a circular cone with base radius of r and slant height l, which is we cut it along the dashed line in figure 1, and then we flattened it into a form of a sector of a circle with radius of l and a central angle of theta, which is equal to 2 phi r over l. Therefore, we define the lateral surface area of a cone to be A equal to phi r l. The area of the band or frustum of a cone with the slant height L and upper and lower radius R1 and R2 is found by subtracting the areas of two cones, which we have this equation from similar triangles, and then we have this equation, and then putting this equation into another form, and then we get the final exact of the equation, which is A equal to 2 phi r times L. Now we apply this formula to our strategy. Consider the surface shown in this figure, which is obtained by rotating the curve y equal to fx, a less than or equal to x, and x is less than or equal to b about the x-axis, where f is positive and has a continuous derivative. And in this case, we got these equations, or with the Leibniz notation for derivatives, this formula becomes this. Discuss about the triple integral in Cartesian coordinates. Consider the case when a three-dimensional region U is a type 1 region and a straight line parallel to the z-axis intersects the boundary of the region U in no more than 2 points. If the region U will be bounded below by the surface z equal to z1, which is x, y, and above by the surface z equal to z2, which is x, y, shown in figure 1. And then this is the projection of the solid U into the xy plane is the region D. We suppose that the function z1, which is x, y, and z2, which is x, y, are continuous in the region D. Then, for any function of f, which is the x, y, z, is continuous in the region U, we can write the relationship like this.
So, in this video I'm going to do a triple integral in spherical coordinates. So basically it says to go from a regular Cartesian coordinates to spherical coordinates, you have to replace x with its normally to rho. I'm going to call it p. So replace x with p sine phi cosine theta, y with p sine v sine theta, and then z will replace that with p cosine phi. And then we have to multiply all of that by p squared sine phi dp d theta dv. So again, in spherical coordinates, we describe a point diverse coordinate p or rho. I'm going to call it p, that represents length to go out. Okay, so we go out some distance. Theta is the angle made in the xy plane, and then this angle v is going to be the angle made with the positive z-axis.
So this is the first problem, which is the triple integral of the cylindrical coordinates. First thing we need to do is to see these three functions and above the xy plane and between the cylinders. Okay, and this is the rough sketch of the three functions. And this is the conversion function of the x, y, and x. And z, this is the equation for the z. The x is substituted for the r cos theta. And then these are the boundaries, z, r, and theta. Z equals from 0 to r cos theta plus 2, 0 to r cos theta plus 2, which is the line. And the r is from 1 to 2, which is the shaded area, and 0 to 2 phi, which from y-axis comes back to the y-axis. And this is the solution for the first problem. After you have already done the boundaries, you just put it inside the integral. And for the next one, this is the problem for the triple integral of the spherical coordinates. And the first thing you need to do is to see this equation and to draw it out. And this is the equation. This is the rough sketch of the x squared plus y squared plus z squared equals to 1. And we have to also do the functions, the conversion functions, z, x, and y. And the boundaries for the rho is from 0 to 1, which is the radius. Phi is from 0 to 2 phi, which is actually the angle of the xy plane. And this angle is from 0 to 90 degrees, which it is. And this is probably the solution. It isn't actually very hard.
That is for the video.
Thank you for watching.
اللهم اغفر له وارحمه وآفه واعف عنه وأكرم نزوله ووسع مدخله واغسله بالماء والثلج والبرد ونقيه من الخطايا كما ينقى الثوب الأبيض من الدنس وأبدله. اللهم اغفر له وارحمه وآفه واعف عنه وأكرم نزوله ووسع مدخله واغسله بالماء والثلج والبرد ونقيه من الخطايا كما ينقى الثوب الأبيض من الدنس وأبدله. اللهم اغفر له وارحمه وآفه واعف عنه وأكرم نزوله ووسع مدخله واغسله بالماء والثلج والبرد ونقيه من الخطايا كما ينقى الثوب الأبيض من الدنس وأبدله.